Imagine this. The box you threw away yesterday could be back in the store tomorrow, just in a different form. How does an old pizza box turn into a sturdy new box for a smartphone? The secret lies in giant machines that work like steel beasts. They tear cardboard into fibers, cook it in vats the size of a swimming pool, and at temperatures over 350 degrees Fahrenheit, transform it into a wavy, three-dimensional sheet. It's an endless cycle, from the trash can to the factory and back to the store shelves. But there's a detail that almost no one guesses, and you'll only find it out at the end of this video. The main ingredient for producing cardboard is, of course, wood fiber or cellulose. But the main trick is that today, the vast majority of this fiber is secondary. The main source of raw material for new boxes is old cardboard boxes. Imagine this endless cycle. When you throw away a box from a pizza or a new TV into a special container, its journey doesn't end. It's just beginning. Millions of such boxes are collected across the country and taken to paper recycling plants. There, they are dumped into a huge vat called a hydropulper. This is essentially a giant kitchen blender the size of a swimming pool, filled with hot water. Huge blades mix this mass, and the cardboard, soaking, breaks down into individual cellulose fibers, turning into a thick, gray-brown slurry called pulp. During this process, all foreign impurities are removed from the pulp: plastic tape, metal staples, glue residues. Then this mass is thoroughly washed and cleaned to obtain a clean, ready for a new life cellulose fiber. This is the heart of our future cardboard. But secondary fiber cannot live forever. With each recycling cycle, the cellulose fibers become a little shorter and weaker. Imagine you're copying a copy. With each time, the quality drops a little. To maintain strength, fresh blood, primary cellulose fiber, must be added to this recycled mass. And this is where we finally get to the forest. But these are not the ancient forests we see in movies. The raw material for primary cellulose is usually either waste from sawmills, such as wood chips and sawdust left after board production, or fast-growing tree species, like pine, which are grown on special, managed forest farms. This is similar to growing corn. Trees are planted, they grow quickly, they are cut down, and new ones are immediately planted in their place. This wood is also turned into chips, cooked in chemicals to dissolve the natural glue, and turned into a pure cellulose mass. And so, at the paper mill, these two streams, a huge river of recycled fiber and a smaller stream of fresh, are mixed in ideal proportions. This liquid pulp is then poured onto a huge screen, where water is squeezed out of it, and it turns into an endless ribbon of paper, which is then wound into those same giant rolls, ready to become new boxes. At the paper factory, it all starts with 3 giant rolls of paper, each weighing several tons. 2 rolls are flat liner paper, and 1 is paper for the wavy layer. A giant, dense roll of brown paper, called medium. Its edge is fed into a true steel beast, which is the heart of the entire corrugator. This is the corrugating press. The main actors here are 2 huge, massive cylinders of hardened steel, installed one above the other. Their surface is covered with perfectly machined, gear-like grooves, or flutes. The teeth on one roll fit perfectly into the depressions on the other, like 2 perfectly matched gears. And these rolls don't just rotate. They are heated from the inside with steam to a temperature of about 350 degrees Fahrenheit. Before the paper enters these fiery embraces, it is passed through a system of sprayers that douse it with hot steam. This is done to slightly moisten and soften the wood fibers in the paper, making it more plastic and pliable. It's like warming up clay in your hands before you start sculpting. The prepared, slightly moist and warm paper is drawn at a frantic speed between these 2 hot-toothed rolls. With a deep, powerful hum and the hiss of steam, the machine does its job. The teeth of one roll press the paper with incredible force into the depressions of the other. At this moment, under the influence of pressure and heat, the paper fibers don't just bend. They change their structure, forever remembering their new, wavy shape. This happens in a fraction of a second. What flew into the machine as a flat, characterless sheet On the other side, flies out as a perfect, resilient, three-dimensional wave. Immediately after the paper flies out of the hot embraces of the corrugating rolls, it, already in the shape of a perfect wave, continues its movement. Without losing a second, it passes under a glue unit. This is a high-precision device where a special roll, called an applicator, rotates in a tank of glue. This glue is not just any glue. This is a specially prepared mixture based on cornstarch, which is activated by heat. The applicator roll has a perfectly smooth surface and applies a thin, barely noticeable layer of glue only to the very tops of the newly created waves. At this very moment, from another giant roll located above, a flat liner paper is fed. It descends onto the glue-coated waves, and this whole two-layer structure is immediately clamped between the corrugating roll and another, smooth pressing roll. The heat and pressure instantly bake the glue, and a single-sided corrugated cardboard is born. Essentially, a flexible sheet with one flat side and one wavy side. This semi-finished product on a long inclined conveyor, called a bridge, rises up where it accumulates, creating a buffer that allows the first and second halves of the machine to work at slightly different speeds. Next, this single-sided corrugated cardboard descends, and the process repeats. Another glue unit applies glue to the open tops of the waves, and from a third giant roll from above, a second flat layer of liner paper is fed. Now our three-layer pie is fully assembled, but the glue in the second seam is still wet. It enters the longest part of the corrugator, the drying section, or double backer. This is a long, sometimes over 100 feet, horizontal tunnel consisting of a series of flat, steam-heated steel plates. On top of our cardboard sandwich presses a heavy moving belt, pressing it against the hot plates. Under the influence of heat and pressure, the starch-based glue undergoes a process called gelatinization. It swells and turns into an incredibly strong gel, permanently gluing all three layers into a single, rigid and resilient sheet. At the exit of this long machine, we have an endless, perfectly flat sheet of corrugated cardboard. This sheet first passes through a slitter-scorer machine. Here, disc knives cut it lengthwise into several strips of the required width. For example, from one wide sheet, 3 narrower blanks for boxes are made, and special dull wheels, scorers, press lines of future folds on it. Immediately after this, a flying knife works, a giant blade that moves in sync with the speed of the cardboard and chops it crosswise into large rectangular blanks, called blanks. These blanks are automatically stacked into high, even piles. Next, these piles are sent to a converter line, for example, to a flexo-folder gluer machine. Here, the blank first passes through a printing section, where rubber clichés apply logos and text. Then it goes under a slaughter, a set of knives that cut out grooves that separate the future flaps of the box. Immediately after this, the machine folds the blank along the central line and applies a strip of cold glue to a special side flap. The final rollers press this seam, and a finished but flat, folded box flies out of the machine. This final touch, gluing or sometimes stitching the side seam, completes the process. The finished flat boxes are collected, automatically counted, and stacked into bundles, which are then tied with a strap and ready to be sent to the warehouse, where they will wait to become a home for any product in the world. Every year, over 25 billion square feet of oriented strand board are produced worldwide. Imagine, this amount would be enough to cover the entire state of Delaware. Twice. Or to build a path around the Earth over 190 times. Plywood was once the king of the market, but the 80s changed everything. And today, OSB controls over 75% of American construction. But how is a material that changed the industry forever, born from young trees, through hot baths, giant graters, and infernal presses? Watch closely. At the end, you'll learn a secret that even builders keep quiet about. It all begins not in a waste warehouse, but in the forest. For the production of high-quality oriented strand board, Preference is given not to random offcuts, but to whole logs, usually from relatively young, fast-growing trees like aspen or southern yellow pine. These forests are often managed and self-sustaining, which makes the process more environmentally friendly. When the logs, tens of feet long, arrive at the factory, they are not immediately sent to the workshop. First, a hot bath awaits them. They are immersed in long pools of hot water, or placed in chambers where they are treated with steam. This isn't just washing. This process, which lasts several hours, softens the wood, and most importantly, weakens the bond between the wood and the bark. After this sauna, the logs go to a debarking machine. Imagine a huge rotating drum with protrusions inside. The logs rubbing against each other and against the walls of the drum, and the bark flies off them like a husk. Bark removal is a critically important step, as bark lacks strength and does not glue well, so it is an undesirable impurity in the final product. Annually, factories in North America produce over 25 billion square feet of oriented strand board. This number is so absurd that it's hard to comprehend. Let's try. If you took all this quantity of panels and laid them out, you could completely cover the entire territory of the state of Delaware. Twice. Or build a continuous 1-foot wide path that would wrap around the Earth at the equator over 190 times. This is not just a lot, it's total domination. For decades, plywood was the king of the market. But in the 80s and 90s, this daring newcomer came onto the scene, and today oriented strand board controls over 75% of the sheathing market for walls and roofs in residential construction in the United States. This was a real quiet revolution. The cleaned, light, and still damp trunks are ready for the main event, transformation into thousands of thin ribbons. They go to a machine called a strander, or a flaker. This is the heart of the whole process. Imagine a giant metal disc rotating at a frantic speed, equipped with dozens of sharp, scalpel-like knives. The log is slowly fed to this disc, and it shaves off long, flat, chip-like ribbons, strands. This is not chaotic shavings. Each strand has parameters precisely set by engineers. The length can reach 6 inches, the width, about an inch, and the thickness, only a few hundredths of an inch. It is this geometry, this noodle shape, that is the key to the future strength of the oriented strand board panel. When ordinary boards are made from a log, a significant part of it, up to 50%, turns into sawdust, offcuts, and shavings. And in the production of oriented strand board, from 85 to 95% of the entire wood of the log is used. We will talk about this later, but practically nothing goes to waste. The strands are cut from the entire length, and the bark, sawdust, and the smallest particles are burned in furnaces to provide energy for the factory itself. This makes this material not only cheaper, but also much more environmentally responsible. The resulting mass of wet, fresh chips, resembling a huge pile of light noodles, is stored in special bunkers, and from there, it is sent for drying. This is a huge, multi-story drum, slowly rotating, half a football field long. Inside it, a high temperature is maintained, and while the strands are slowly tumbling, moving from one end to the other, a stream of hot air evaporates the excess moisture from them. The moisture needs to be reduced from 50 or 70% to only 2 or 3%. This is absolutely necessary so that the resin can properly soak the wood and glue it firmly. After drying, the strands pass through a system of huge vibrating screens, which sift out particles that are too small, for example dust, which will go to fuel for the same dryer, and pieces that are too large, which will be sent for regrinding. Now the perfectly dry and sorted strands are ready for impregnation. They enter a huge, slowly rotating drum mixer. While they are being mixed, a sticky chemical cocktail is sprayed onto them through special nozzles. The main ingredient is a waterproof resin, which will be our glue. The second important component is paraffin wax. It envelops each chip like an invisible raincoat, and it is this that will give the future-oriented strand board panel its famous moisture resistance. And now, the smartest and most important part of the process begins, which gave the material its name, orientation. The strands, impregnated with glue and wax, go to a long, wide-forming conveyor. Here, a whole system of mechanical choreographers works. Special discs, rollers, and combs that lay out the chips in a precisely defined order. First, the bottom layer is formed. The choreographers lay out the strands so that they all lie parallel to the long edge of the future panel, that is, lengthwise. Then comes the turn of the middle layer. Here the strands are laid out perpendicularly, that is, crosswise. And finally, the top layer is again laid out lengthwise. As a result, we get a thick, fluffy, 3-layer pie, where the fibers in each layer are perpendicular to the fibers in the adjacent one. It is this cross structure, which imitates the strength of plywood, that is the secret that makes oriented strand board incredibly strong in bending and resistant to deformation. This fluffy mat, which can be several feet thick, slowly moves to the final test, the hot press. This is a real industrial leviathan, a multi-story structure that creates colossal pressure and heat. The mat enters inside, and massive steel plates begin to compress it with a force of hundreds of pounds per square inch. At the same time, the press is heated to a temperature of 400 degrees Fahrenheit. This heat activates the resin, causing it to polymerize and permanently glue all the chips into a single monolithic shield. The wax also melts, even better impregnating the wood and filling microscopic voids. In a few minutes, the loose mass turns into a hard, incredibly dense, and hot panel. A huge master sheet comes out of the press, which can be 50 feet long and 12 feet wide. While it is still warm, its edges are trimmed with diamond saws, and then giant saws cut it into standard building formats, most often 4 by 8 feet. Markings with information about its thickness, class, and compliance with building codes are applied to the surface of the panel. Sometimes special tongues and grooves are cut into the edges so that the sheets fit together perfectly when installing a floor or roof. The finished, perfectly rectangular sheets are stacked in high piles by robotic manipulators, wrapped in protective film, and sent to the warehouse. And so, having passed the path from a whole log through a giant grater, a sticky shower, and the fiery embrace of a press, this honest, unpretentious, and insanely strong material is born, ready to become the silent but reliable foundation for thousands of homes across the country. For the construction of an average single-family home with an area of 2,400 square feet, approximately 8,000 square feet of oriented strand board panels are needed. This material goes into everything. They sheathe the exterior walls, creating a strong and rigid frame. They make a solid sheathing on the roof, on which shingles are then laid. And of course, they make the subfloor, which is the foundation for all rooms. In essence, the entire modern American house is a wooden frame wrapped in a strong cocoon of oriented strand board. Every year, hundreds of millions of square feet of hollow core slabs are born worldwide. That's an area large enough to build 30 pentagons. Imagine a factory where a machine crawls along a 600-foot track, slowly creating a concrete ribbon half a mile long in a single shift. And now for the main point. These slabs are a whole 2,000 tons lighter for a building with an area of 100,000 square feet. That's a minus 500 elephants on the construction's weight scale. But how can such a light slab be so strong? In this lies the hidden secret of engineers, which you will learn if you watch until the end. The slip former machine crawls along a 600-foot forming bed at a speed of about 4 feet per minute. Doesn't sound very fast. Now let's do the math. That's 240 feet per hour. That's almost the length of an Olympic swimming pool being born from concrete in less than an hour. In a single 10-hour shift, one such bed can spit out almost half a mile of perfectly formed concrete slab. And at a large factory, there can be several such beds. This isn't just construction. It's an assembly line working at a speed unimaginable for traditional on-site concrete casting. And now for the main feature, the hollow cores. These holes inside are not just for aesthetics. They reduce the weight of the slab by almost 50% compared to a solid slab of the same thickness and strength. What does this give us? Here's what. Imagine the construction of an office center with an area of 100,000 square feet. If the floors were made of ordinary solid concrete, their weight would be approximately 5,000 tons. But with hollow core slabs, only 3,000 tons. We just threw out 2,000 tons of excess weight from the building. That's the weight of about 500 adult elephants, which now doesn't need to be supported by the foundations, columns, and beams. This allows for making the entire structure of the building lighter, more elegant, and most importantly, much cheaper. But how can such a light slab be strong? The secret is in those tensioned steel muscles. The concrete used in these slabs is not the same as on your sidewalk. This is high-strength concrete that can withstand a pressure of over 8,000 pounds per square inch, while ordinary concrete is only 3,000 or 4,000. And the steel strands inside it are tensioned with such force that they create a constant compressive force in the slab. Thanks to this, a hollow core slab can easily span a length of 60 feet without any intermediate support. 60 feet is the width of a professional basketball court. Imagine a huge open space without a single column. That's why these slabs are beloved for the construction of parking garages, supermarkets, and open-plan offices. Annually in North America, over 200 million square feet of hollow core slabs are produced. This number is simply mind-boggling. This is an area large enough to build 30 giant buildings like the Pentagon. Every year. This isn't just a building material. This is a whole industry built on speed, efficiency, and the smart use of resources. So these figures are not just dry data. They are proof that sometimes, to become stronger, you just need to get rid of the excess inside. It all begins not in a concrete mixer, but on a giant, perfectly flat airfield inside the workshop. This is a forming bed. Imagine a perfectly smooth, polished steel track several feet wide, but with a length of 400, 500, and sometimes even 600 feet. This is longer than 2 football fields laid end to end. Under this track, pipes are laid, through which hot water or steam circulates to keep it warm. This is our ideal bed for the birth of the future giant. At both ends of this track are massive steel anchors, embedded in a thick concrete foundation. They look like steel teeth that have bitten into the ground, and their task is to withstand simply inhuman loads. Between these two anchors, high-strength steel strands are stretched. This is not ordinary wire. It's several steel threads woven together, each of which can withstand the weight of a car. They are laid along the entire length of the 600-foot bed, forming the future skeleton of the slab. One end of each strand is securely fixed in the anchor, and, to the other, a giant hydraulic jack is connected. And this jack begins to pull. It tensions each of these steel strands with a force of 30 or 40,000 pounds. It's like hanging 3 full-size pickup trucks on each thin thread. The steel muscles tense up, becoming as hard as the strings of a giant guitar, and store colossal energy within them. This is secret number 1. Pre-stressing. When the steel skeleton is tensed and ringing from the tension, the main hero comes on stage. The forming machine, or slip former. This is one of the most amazing machines in the world of construction. Imagine a strange, low-slung, self-propelled creature that slowly crawls on rails along our long bed. On top of it is a large hopper where concrete is loaded. But this is not ordinary liquid concrete. This is so-called zero-slump concrete. It is so dry that it resembles damp earth. If you took it in your hands, it would not flow. And so this machine begins its slow journey. Inside it, a real miracle happens. First, the concrete from the hopper is fed down and surrounds our tensioned steel strands. Second, special vibrators and compactors with incredible force tamp this dry mixture, making it incredibly dense. And third, most importantly, inside the machine are special forming tubes, or mandrels, which, vibrating, pass through the thickness of the concrete, leaving behind perfectly round, smooth, hollow cores. The machine, like a giant concrete snail, slowly crawls forward, and behind it, like a trail, remains a perfectly formed, endless concrete slab, with hollow cores inside and tensioned steel muscles hidden in its body. Because the concrete is so dry, it instantly holds its shape and does not spread. This is secret number 2. The hollow cores that make the slab 50% lighter than a solid one, while barely reducing its strength, because the main work is done by the top and bottom flanges. When the machine reaches the end of the 600-foot bed, its work is done. But our slab is still green and weak. It's time for a spa procedure. Workers cover the entire length of this concrete ribbon with huge insulating tarps, similar to blankets. Hot steam is fed under these blankets. This creates a sauna effect that sharply accelerates the chemical reaction of concrete hardening. Under normal conditions, concrete needs weeks to gain full strength, and in this hot, humid atmosphere, it reaches the required strength, over 5,000 pounds per square inch, in just 12 or 24 hours. When the concrete has hardened and become as strong as stone, the moment of release comes. Workers slowly release the tension on the hydraulic jacks. The tensioned steel strands, which are now firmly bonded to the concrete, try to contract to their original length, but the concrete does not let them do so. As a result, this huge compressive force is transferred to the concrete slab itself. Now, it is not just concrete, it is pre-stressed or compressed. This means that when a load is applied to it from above, trying to bend it, it will first have to overcome this built-in compressive force. This is what allows it to span huge distances without additional supports, and the final act of this spectacle is cutting. Along our long concrete ribbon, a giant saw moves on rails. This is a monster with a huge disc coated with industrial diamonds. With a deafening roar and a fountain of sparks and water that cools the disc, this saw with incredible precision cuts the slab into pieces of the required length, according to the order. The finished, perfectly even, light, and incredibly strong slabs are picked up by giant cranes and loaded onto trucks. And so, having passed the path from a tensioned steel string to the slow crawl of a concrete snail and the final diamond cut, this brilliant work of engineering is born, ready to become a fast, effective, and reliable floor in the buildings where we live, work, and play. Every year, over 1 billion square feet of laminate flooring are sold worldwide. We see this covering every day at home, in offices, and even in shopping malls. But few people realize the complex engineering hidden in each plank. Imagine, under a pressure of over 1,000 pounds and at a temperature higher than 400 degrees Fahrenheit, thin layers of paper and resin are transformed into an ultra-durable surface that challenges stone itself. The laminate market is valued at tens of billions of dollars, but behind these numbers is a process that is impressive in its scale and precision. Watch until the end, and you'll discover the secret that your floor is hiding. Laminate, which has become an extremely popular choice for flooring, combines aesthetics, durability, and cost-effectiveness. Its production begins with the careful selection of raw materials and ends with the creation of finished panels, ready for installation. For the manufacture of laminate, 4 main components are used: the substrate, a stabilizing layer, decorative paper, and a protective layer. Each of these elements plays a key role in the formation of the final product. The process begins with the preparation of the core, or the base of the laminate, which is the most important part that provides its strength and stability. This core is made from a high-density fiberboard, known as high-density fiberboard. The production of HDF begins with sawing wood, mainly coniferous species, into small chips. These chips then undergo a steaming and cleaning process to remove foreign impurities. After this, the wood is transformed into fibers using special mills. The resulting fibers are mixed with glue, most often based on synthetic resins, and formed into a thick, soft mat. Next, this mat undergoes hot pressing under a pressure of about 700 pounds per square inch at a temperature of 400 degrees Fahrenheit. This pressing compacts the fibers, forcing out moisture and air, and creates a strong, uniform HDF board. The thickness of such boards is usually from 1/4 of an inch to 1/2 an inch, depending on the laminate class. The quality of the board directly affects the moisture resistance of the finished laminate, its bending strength, and overall durability. The next important stage is the preparation of the decorative and protective layers. The decorative layer is a special paper on which a printed pattern is applied, imitating wood, stone, or another material. This paper is impregnated with melamine resin, which, after polymerization, gives it hardness and wear resistance. The protective or overlay layer is also paper, but it is impregnated with an even greater amount of melamine resin and small particles of aluminum oxide. Aluminum oxide, which is a very hard material, gives the laminate its main property: resistance to abrasion and scratches. The thickness of the protective layer is only a few thousandths of an inch, but it performs a critical function. Both of these impregnated paper layers are dried and stored in rolls until the pressing moment. The third layer, the stabilizing or balancing layer, is placed on the lower side of the base. This layer also consists of paper, impregnated with resin, and serves to prevent the board from warping. Without this layer, during use, the difference in pressure and humidity between the upper and lower layers of the laminate could lead to the panel bending. The stabilizing layer helps to maintain the geometric stability of the board. The key moment in the production of laminate is the hot pressing process, which combines all 4 components into a single monolithic panel. This takes place on multi-layer presses, where the prepared sheets are assembled into a sandwich. First the stabilizing layer, then the core. After that the decorative layer, and on top, the protective overlay. This multi-layer structure is placed in a press where, under the influence of high temperature, which can reach 420 degrees Fahrenheit and a pressure of 1,200 pounds per square inch, the melamine resins melt and harden, securely bonding all the layers together. This process takes from 30 to 40 seconds and is called lamination. During pressing, the surface texture is also formed, which can imitate the texture of wood. After pressing, the laminate sheets are cooled and stabilized, which is important to prevent deformation. When the panels have cooled, they are sent for trimming and milling. At this stage, the large sheets of laminate, which can be 8 feet by 4 feet in size, are cut into smaller, standard-sized panels. For example, 48 inches by 6 inches. After trimming, locking joints, known as a click system, are milled on the side edges of each panel. This is a key feature of modern laminate, which allows it to be laid without using glue. The milling process must be extremely precise to ensure a perfect connection between the panels. Tolerances are only a few thousandths of an inch. The final stages of production include quality control and packaging. Each batch of laminate is tested for abrasion resistance, impact resistance, moisture resistance, and other parameters. The abrasion resistance test, known as the Tabor test, determines the wear class of the laminate. A high class means that the laminate will withstand a greater number of abrasion cycles. After successfully passing all tests, the panels are sorted, packed in sturdy cardboard boxes, and prepared for shipment. The weight of one box can be 40 pounds. All these processes, from the transformation of wood into fibers to the packaging of finished panels, are part of a highly automated and technologically complex production cycle. The result is a laminate that not only has an attractive appearance, but also high performance characteristics, which makes it one of the most popular flooring options in the United States and around the world. The total length of a production line can reach hundreds of feet, and the production speed is measured in thousands of square feet per hour. Understanding these processes helps to appreciate the complexity and engineering excellence of the product that we see every day in homes, offices, and commercial spaces. The global laminate flooring market has shown stable growth in recent years, driven by its popularity as an affordable, durable, and aesthetically attractive covering. According to expert estimates, it is projected that by 2030, this figure will grow to $35 billion, demonstrating an average annual growth rate of about 4%. The main driving factors are the construction boom in developing countries and the growing popularity of do-it-yourself repairs in developed countries. The geography of production and consumption. The largest regions for laminate production and consumption are the Asia-Pacific region and North America. In the United States alone, the annual production of laminate reaches billions of square feet. Europe also remains a significant player in the market, but the growth rates there are somewhat slower. Approximately 40% of the global demand for laminate comes from the residential sector, while the remaining 60% is from the commercial and industrial sectors. A significant amount of wood raw material is used for the production of laminate. Typically, to produce 1 square foot of high-density laminate board, approximately 0.15 cubic feet of wood is required. Given the production volumes, this leads to significant consumption of forest resources, although most manufacturers use recycled wood or waste from the sawmill industry. Standard sizes of laminate planks in North America range from 48 to 60 inches in length and from 5 to 8 inches in width. The weight of one package can be from 35 to 45 pounds, depending on the thickness and density of the material. In the modern market, there is a growing demand for laminate with a high imitation of natural wood and stone. Over 70% of sales are for decors that imitate wood, with oak and maple shades being the most popular. The demand for water-resistant laminate is also growing, which occupies over 25% of the market and continues to increase its share, especially for use in kitchens and bathrooms. The next time you walk on your laminate floor, remember this epic story. So enjoy your renovated space. Imagine a toxic gas that was once used as a weapon in war. Today, however, your plastic windows, the medicines in the pharmacy, or even your drinking water wouldn't exist without it. The United States produces over 12 million tons of chlorine each year, a capacity that could turn the ocean into a giant swimming pool in a matter of days. But the real mystery is something else. Only a tiny fraction of this volume is used for disinfection. So where does the rest go? Watch until the end, and you will learn a secret that will turn your idea of this gas upside down. The United States is one of the world's largest producers of chlorine. Annually, the country's factories produce over 12 million tons of this gas. This number is simply mind-boggling. Imagine the weight of the aircraft carrier Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 such aircraft carriers weigh. This huge amount makes chlorine one of the 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. But it's not brought to the factory in salt shakers. It is either mined in the form of huge blocks, or, much more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated salt solution called brine. And it is this concentrated, salty as tears solution that is our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals that can clog our expensive equipment. So before the main show begins, the brine undergoes a thorough cleaning. It is passed through a whole series of tanks where, with the help of chemicals, all impurities are precipitated and filtered out of it. At the exit, we get a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. Now let's move to the heart of the factory, to the so-called cell room. This is a huge, noisy hall, filled with rows of strange closed tanks connected by a network of pipes and thick electrical cables. These are electrolyzers, or cells. It is here that all the magic, or rather, all the chemistry, will take place. Let's imagine one such electrolyzer. Essentially, it's a box into which our clean salt solution is poured, and two electrodes are immersed in this solution, a positively charged anode and a negatively charged cathode. And now, a direct electric current of colossal strength is applied to these electrodes. And here the breakdown begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions, and the electric field forces them to move. The positive sodium ions are attracted to the negative cathode like a magnet, and the negative chloride ions to the positive anode. And here, at the anode, what it was all for begins. Each chloride ion that has stuck to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, approximately 2,500 kilowatt hours of electricity are needed. And now let's multiply this by 12 million tons per year. It turns out that this industry consumes about 30 billion kilowatt hours annually. This is more than the annual electricity consumption of entire states, like Vermont or Wyoming. This is a city of 1 million people, working all year just to break salt molecules. But what happens at the cathode? The sodium ions have arrived there. But they do not turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. This is our first byproduct. And the hydroxide ions remaining in the solution combine with our sodium ions, forming caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We have just obtained 3 substances: chlorine, hydrogen, and caustic soda. And they must never be mixed. Chlorine and hydrogen together form an explosive mixture. And chlorine and caustic soda react to form bleach, which we don't need at all. Therefore, the whole genius of the technology lies in separating these 3 products at the moment of their birth. For this, special membranes or diaphragms are used. Imagine that between the anode and the cathode, there is a thin, paper-like, but very clever partition. This membrane, made of a special polymer, is like a face control at a nightclub. It lets the positive sodium ions pass through to the cathode, but blocks the negative chloride ions, not letting them into the cathode space. Thus, chlorine is born and collected in one part of the cell, and hydrogen and caustic soda in the other. Now we need to collect our harvest. From the anode chamber, a wet, hot, greenish-yellow gas is continuously pumped out. First, it needs to be cooled. It is passed through heat exchangers, where it gives up its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there is one substance it doesn't touch: concentrated sulfuric acid. So the wet chlorine is passed through towers, where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cold, but still gaseous chlorine is ready for the next stage: liquefaction. It is compressed under huge pressure and simultaneously cooled. Under this double blow, the gas turns into a transparent, amber-yellow liquid, similar to oil. This liquid chlorine is much more convenient to transport and store. It is poured into special thick-walled steel tanks or railway cars. Every step of this process takes place in conditions of absolute hermeticity, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the plant itself or sold for the production of ammonia or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. This is one of the most important products in the chemical industry, used for the production of soap, paper, aluminum, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, people have learned to obtain 3 extremely important substances at once, which are the foundation for thousands of other products that surround us in everyday life. And now, let's see where all this huge amount of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So, where does the other 95% go? It is a key building block for other products. About 40% of all chlorine goes to the production of this universal plastic. The vinyl windows in your house, water pipes, medical IVs, vinyl records, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% is used to create thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides. The list is endless. And chlorine is also a key component for bleaching paper, giving it that same pure white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other may rise, allowing the plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy, from the plastic pipes under our streets to the medicines in our pharmacies. Today, we're embarking on a journey to one of the coolest and smartest factories in the world of woodworking. We're going to talk about how people looked at ordinary wooden floors, which fear moisture like a vampire fears garlic, and said, "Dude, we can do better." Thus, engineered hardwood was born. This isn't just a board, it's a true wooden club sandwich, a brilliant work of engineering where the beauty of natural wood is combined with superhuman stability. This is the story of how a floor that laughs in the face of humidity fluctuations is born from several different trees, a giant glue juicer, and an infernal ultraviolet tanning session. It all begins not with one, but with 2 different forests. The first forest is a runway for supermodels. Here grow those noble trees whose beauty makes the heart beat faster. Majestic oak, strong hickory, elegant maple, or luxurious American walnut. For our sandwich, we don't need the whole log. We only need its soul, its most beautiful part, the thin top layer that everyone will see. Therefore, the best, straightest logs are brought to the factory. First, a real spa day awaits them. They are immersed in huge pools of hot water, or placed in chambers where they are treated with steam at a temperature of 200 degrees Fahrenheit. This is done to soften the wood and make it ready for the thinnest slicing in the world. After this, the log goes to a machine that is something between a giant pencil sharpener and an industrial slicer for delicacies. This is a peeling or slicing machine. Imagine a sharp, scalpel-like knife 10 feet long. It is slowly brought to the rotating log and begins to shave off a continuous wide ribbon of wood, just 1/8 or even 1/16 of an inch thick. This is our veneer, our precious ham for the sandwich. This wet, flexible sheet is then carefully dried in special chambers to make it stable, but to preserve its natural beauty. But what will be the bread in our sandwich? For this, we don't need supermodels. We go to another forest where simple workhorses grow. Fast-growing and inexpensive species like poplar, birch, or eucalyptus. These logs go through a similar peeling procedure, but the ribbons are cut a little thicker. And this is where the main secret of the stability of engineered hardwood begins. Imagine that you took several of these thin wooden sheets. You lay the first one so that the fibers run lengthwise. You lay the second layer on top, but you turn it 90 degrees so that the fibers run crosswise. The third, again lengthwise. The fourth, again crosswise. And so on, creating a multi-layered pie where each layer is perpendicular to the previous one. Why is this so important? Because wood is alive. It always tries to expand and contract across the grain, reacting to humidity. But when you glue these layers perpendicularly, they seem to hold each other in a steel embrace. One layer wants to expand, but the other, lying perpendicularly, does not allow it to do so. This is a brilliant solution that makes the base of engineered hardwood incredibly stable and resistant to deformation. This multi-layered pie of cheap wood is sent under a hot press, where under huge pressure and temperature, it is glued into a single, strong block, like plywood. These are the muscles of our floor. Now it's time to assemble our club sandwich. We have the sole, a thin, beautiful veneer of expensive wood. And we have the muscles, a thick, stable base of cheap wood. They need to be connected. The base moves along a conveyor and passes under rollers that resemble giant paint rollers. These rollers generously pour a special, incredibly strong glue onto it. Our precious veneer is carefully laid on top of this sticky surface, and this whole structure is sent to the final hot press. With a force of hundreds of pounds per square inch, the press connects beauty and strength into a single whole. At the exit, we get a huge master sheet, from which individual boards will then be cut. But this is not a floor yet, it's just a blank. It's time for makeup and a manicure. Giant saws cut the large sheet into individual boards of standard width, for example, 5 or 7 inches. And here, each board goes to one of the most important machines, the milling machine. An incredibly complex system of mills and knives, rotating at a frantic speed. On one side of the board, they cut a long protrusion called a tongue, and on the other, an equally long groove called a groove. It is this system that will allow the boards to fit together perfectly during installation, forming a continuous, smooth surface without gaps. Now our board has the correct shape, but its surface is still a bit rough. It is sent for sanding. This is a whole line of several sanding machines, each of which uses finer and finer sandpaper. After this process, the surface of the board becomes as smooth as silk, ready for the final coating. And here, the real high-tech begins. The board enters a finishing line that looks like a car wash, only instead of water and soap, there is varnish and ultraviolet light. First, rollers apply the first layer of a special, incredibly durable varnish based on aluminum oxide. This is one of the hardest substances in the world, which makes the floor resistant to scratches. Immediately after application, the board passes under powerful ultraviolet lamps, and the varnish, which in normal conditions would dry for hours, hardens in a fraction of a second under the influence of ultraviolet light. Then a second layer is applied, and again a tan under ultraviolet light. The third, fourth, fifth. Sometimes it goes up to 7 to 9 such layers. As a result, we get a perfectly smooth, incredibly strong, and durable coating. That ultraviolet coating is not just a varnish. Aluminum oxide is added to its composition, one of the hardest minerals in the world, second only to diamond. From 7 to 9 layers of this coating are applied to the board, and each layer is instantly baked by ultraviolet light. As a result, we get a surface that is many times more resistant to scratches and wear than a traditional varnish applied to a solid board after installation. At the final stage, each board undergoes strict quality control. Inspectors with an eagle's eye look for any defects, scratches, uneven color, problems with geometry. Only perfect boards get a ticket to life. Robotic manipulators carefully stack them in boxes, indicating the type of wood, color, and dimensions. And so, having passed the path from 2 different forests, through hot baths, sharp knives, sticky waterfalls of glue, and an infernal ultraviolet tan, this brilliant creation is born. Engineered hardwood. It took the best from nature, its beauty, and the best from engineering, its stability, to become the perfect floor for our homes, which is not afraid of either winter dryness or summer humidity. The engineered hardwood market in the USA is a giant that turns over more than $10 billion a year. And this is not just a stable market, it is growing rapidly, winning an increasing share from its older, solid brother, solid wood. Why? Because it's smarter, and the numbers prove it. The main superpower is stability. Thanks to its cross-layered, multi-layered structure, engineered hardwood is 50 and even 60% more stable than a solid board of the same species and thickness. What does this mean in real life? It means that it can be installed where ordinary wood would go crazy from humidity fluctuations, in basements, kitchens, bathrooms, and on a concrete slab. It is not afraid of underfloor heating. If one perfect log of precious white oak was sawn into a 3/4 inch thick solid board, a certain number of square feet of flooring would be obtained. And now, attention! If this same log were used to produce thin veneer for engineered hardwood, 3 or 5 times more finished flooring could be obtained from it. This means that to cover the same area, 3 or 5 times fewer valuable trees need to be cut down. This makes engineered hardwood a much more environmentally responsible choice.